Section: Introduction. In this section, we explore the lack of transparency surrounding large language models like GPT-4, Claude 2, and Gemini. These models are kept secretive due to the competitive nature of the field and concerns about potential attacks. Despite the limited access to their internal details, these models can still be interacted with through APIs. Our focus is on model stealing, which involves extracting model weights by querying the model's API. Our contribution lies in introducing an attack that can recover the complete embedding projection layer of a transformer language model, even when the model is treated as a black box. Unlike previous methods that reconstruct models from the input layer upwards, our attack works in a top-down manner, directly extracting the model's final layer. By exploiting the low-rank nature of the final layer, we can extract crucial information such as the model's width and hidden dimension. Stealing this layer provides insights into the model structure and may aid in future attacks. While our attack only retrieves a portion of the model, the fact that any parameters can be stolen from a production model raises concerns about potential extensions of this attack. By recovering the model's last layer, we can gain a better understanding of the model's overall size and differences between models. Our attack has been successfully applied to models like Google's PaLM 2 and OpenAI's GPT-4, prompting these services to enhance their defenses. We have responsibly disclosed our attack to vulnerable services and have worked with organizations like OpenAI to address any vulnerabilities. Our focus is on high-fidelity attacks, aiming to create stolen models that closely match the target model's performance on all inputs. Previous attacks have focused on specific properties of deep neural networks with ReLU activations, but they are not scalable to production language models due to various limitations. Our attack stands out for its effectiveness and efficiency in extracting crucial information from black box models. Section Summary. In this section, we introduce an attack that can be used on black box language models to recover the complete embedding projection layer of a transformer language model. Unlike previous approaches that start from the input layer, our attack operates top-down by directly extracting the model's last layer, exploiting the low-rank nature of the final layer's projection. By making targeted queries to a model's API, we can extract crucial information like the embedding dimension or the final weight matrix, which can reveal the model's width, reduce its black box nature, and potentially lead to more extensive information recovery. Section: Problem Formulation. In this section, we explore models that take a series of tokens from a vocabulary X as input. We focus on models that are parameterized and produce a probability distribution over the next token based on an input sequence of tokens. The model structure involves a parameterized model f_theta that generates the probability distribution and another parameterized model g_theta that calculates hidden states. Additionally, there is a matrix W and a softmax function applied to the logits to obtain probabilities. The hidden dimension size is smaller than the token dictionary size, where h, LLL. For instance, llama selects h from a set like 4096, 5120, 6656, 8192, and L equals 32,000. On the other hand, models like GPT-4 have a vocabulary of approximately 100,000 tokens. Regarding the threat model, we assume that the adversary lacks extra knowledge about the model parameters. We consider a scenario where there is a model f_theta, provided by a service and accessed by users through an Oracle interface, O. This Oracle is ideal and only reveals information that can be inferred from the input and output data. The adversary cannot gain insights into the model through timing or implementation details of the interface. Various language models offer APIs with different capabilities, affecting the potential for model extraction attacks and the choice of attack strategies. We introduce the logits API as a baseline threat model, where all token logits are provided in response to a prompt. This setting serves as a starting point for developing attack methods that can be applied in more restricted scenarios, such as obtaining log probabilities for only a few top tokens before executing the attack. In the context of the logit vector API's extraction attack, we assume the adversary can access the logits feeding into the softmax function for all tokens in the vocabulary directly. We introduce new attack techniques to achieve high-fidelity extraction of parts of a transformer model. We demonstrate how to determine the hidden dimension H using the logits API and present an algorithm to recover the matrix W. To begin, we implement a simple attack that enables an adversary to uncover the hidden dimension size of a language model by querying the oracle O. By querying the model with various random prefixes, we can observe that the output logit vectors, although L-dimensional, actually lie in an underlying H-dimensional subspace due to the embedding projection. Through a sufficient number of queries, we can identify linear dependencies among the queries and determine the subspace dimensionality, which corresponds to the hidden dimension of the model. The attack is based on a mathematical result where the rank of the matrix composed of query responses from the logit vector API is at least the hidden dimension H. If the matrix with columns G underscore theta, P underscore I, and the matrix W both have rank H, then the rank of the query response matrix equals H. We make practical considerations for numerical precision in computing the rank of the matrix Q and provide an algorithm for this purpose. Experiments demonstrate the effectiveness of the attack in determining the hidden dimension across various models, with accurate recovery in most cases. The attack successfully identifies the embedding size with minimal errors, showcasing its reliability in extracting essential model parameters. Section Summary. In this section, we focus on models that process token sequences and generate probability distributions over the next token. The model structure involves a parameterized function that computes hidden states and an embedding projection matrix, with a softmax function applied to the resulting logits. We assume a threat model where an adversary has access to the model through a perfect oracle API, and we develop extraction attacks to recover parts of the model, such as identifying the hidden dimension and reconstructing the embedding projection matrix. Section. Full layer extraction, up to symmetries. In this section, we extend our attack to retrieve the final output projection matrix, W, that connects the last hidden layer to the output logits. We define Q using algorithm and express it as Q equals U CDOT sigma CDOT V caret T using singular value decomposition SVD. Surprisingly, the matrix U directly represents the final layer, acting as a rotation. We can demonstrate that U CDOT sigma equals W CDOT G for a matrix G of size H times H in a lemma. In the logit API threat model, following the assumptions of the lemma I, our method retrieves tilde W equals W CDOT G for some G in R caret H times H E if G underscore theta P is a transformer with residual connections. Exact extraction of W is not feasible. The experiments involve evaluating the attack success rate for 6 models by comparing the root mean square, RMS, between our extracted matrix tilde W equals U CDOT sigma and the actual weight matrix, considering AH times H affine transformation. The results are presented in a table, showing our reconstruction error is significantly lower than the error between a randomly initialized model and the actual weights. Moving on to the extraction attack for logit bias APIs, we make a crucial assumption that the adversary can access the complete logit vector for each input, which is not typically available in production models. Instead, many APIs offer log probabilities for the top K tokens, along with the option to specify a logit bias for certain tokens. We aim to uncover the full logit vector for different prompt queries using this API. We introduce efficient attack strategies based on token cost and query cost, optimizing for effectiveness while considering the constraints imposed by the APIs. Our techniques involve computing the logit vector for a given prefix P through a series of queries with varying logit biases, addressing the challenges posed by the limitations of production APIs. In summary, our approach focuses on developing practical and efficient attacks for extracting information from models under specific API constraints, ensuring the effectiveness of the extraction process while considering the costs associated with token usage and query duration. Section Summary. In this section, we extend our attack to recover the final output projection matrix, W, mapping from the final hidden layer to the output logits by utilizing the matrix, U, obtained from the singular value decomposition, SVD, of Q. We demonstrate that U directly represents the final layer, and through a lemma, we show that U, CDOT, sigma, equals W, CDOT, G, allowing us to recover an approximation of W in the Logit API threat model. We evaluate the attack success rate by comparing the extracted matrix tilde, W, equals U, CDOT, sigma, with the actual weight matrix, showcasing the efficiency of our reconstruction method. Section. An improved cost optimal attack. In this section, we present an improved cost optimal attack. We can enhance both the query cost and token cost by generalizing the attack. Instead of revealing 4 or 5 logit values for a single generated token, we can send a multi-token query, P_0, P_1, P_2, P_n, and request the logprob vector for each prefix of the prompt, P_0, P_0, P_1, P_0, P_1, P_2, and so on. Initially, OpenAI's API allowed such queries by providing log probs for prompt tokens and generated tokens. However, this feature has been removed, and now we can only see log probs of generated tokens. By making the model emit a specific sequence of tokens, P_n+1, P_n+2, P_n+m, we can inspect the logprob vector of each generated token. To achieve this, we fix a token X and 4 other tokens and make the model emit X, X, X. Instead of giving a logit bias of B for all 5 tokens, we provide a logit bias of B for token X and B, less than B for the other 4 tokens. If B is large enough to bring the other tokens into the TOP5 outputs, we can learn the logits for those tokens. As long as B is small enough for the model to always complete the initial prompt P_0 with token X, we can collect the logits for prompts like P_0, X, X, X. The query cost of this attack is 1/4 meters, where m is the expansion factor. Each query requires 1 plus m tokens, so the token cost is 1 plus m/4 meters. If there is an overhead of delta tokens in the API, the token cost becomes 1 plus m plus delta. When m equals 1 and there is no expansion, the attack reduces to the first attack with a query cost of 1/4 and a token cost of 1/2. Additionally, we discuss an extraction attack for top 1 binary logit bias APIs. Even if the API only returns the top logprob, k equals 1, and the logit bias is limited to 2 values, an attack is still possible. By querying the model twice, once without any logit bias and once with a bias of -1 for token t, we can learn about token t's logprob. The attack requires 1 query and token per logprob extracted, but it may need more queries for accuracy compared to previous attacks due to numerical stability issues. Section Summary. In this section, we propose an enhanced cost-effective attack strategy by generalizing the approach to minimize both query and token costs. By sending a multi-token query and examining log probabilities for each prefix of the prompt, we aim to reduce costs. This method involves forcing the model to emit a specific sequence of tokens to gather logit information efficiently, resulting in a query cost of 1/4 meter and a token cost of 1 plus m, 4 meters, with potential variations based on the expansion factor. Section. Extraction from logprob-free APIs. In this section, we will explain how we can extract information from APIs that do not provide logprobs. Some API providers may restrict access to logit bias and logprobs together to prevent attacks. To overcome this restriction, we have developed logprob-free attacks that can reconstruct the complete logit vector by using binary search on the logit bias vector, although this method is more costly. Some APIs offer a logit bias term without revealing logprobs. We define a function O, P, B, that finds the token with the highest logit value based on a given prompt P, where B represents the logit bias. We use notation like B equals I, Z, to indicate that the bias is set to Z for token I and 0 for others, and B equals means no logit bias is applied. The bias values are assumed to be within the range B, B. Our attacks in this section aim to reconstruct the logit vector with an error margin of var epsilon. We start with a basic logprob-free attack strategy. By setting the logit bias for each token appropriately, we can determine each token's logit value through binary search. This method ensures that we can recover all logits, with a small error due to the softmax function. Although this attack method is not very efficient, it accurately extracts the logit vector. We have proven that our algorithm can output a value within var epsilon of the true logit difference for a token I compared to the most likely token 0 in a limited number of API queries. However, there are limitations to this approach. If the difference between the logit values of token I and token 0 is too large, it becomes challenging to sample token I efficiently without logprob access. We can slightly expand the range for which we can extract logit information by adjusting the biases, but for most models and prompts we consider, this is not necessary. Other researchers have also explored similar methods for extracting logits from APIs without logprob information. Section Summary. In this section, we develop logprob-free attacks that aim to recover the complete logit vector by performing binary search on the logit bias vector, even though this method incurs higher costs. By adjusting the logit bias for each token through binary search, we can reconstruct every token's logit value, with the attacks efficiently extracting the logit vector up to an additive error of epsilon. This approach correctly extracts the logit vector, with the algorithm outputting values that are at most epsilon away from the true logit differences in a logarithmic number of API queries. Section. Improved logprob-free attack, hyperrectangle relaxation center. In this section, we aim to enhance the previous attack method by adjusting the logit bias of multiple tokens simultaneously. We utilize the same API as before, but now with a restriction that the model can accept a maximum of n+1 tokens in the logit bias dictionary. Initially, we run a query to identify the most probable token and assign its index as 0. Our objective is to estimate the difference between the logits of n different tokens compared to the chosen token. If n is less than the total number of tokens minus 1, we repeat the algorithm for different batches of n tokens multiple times. Our method involves querying the API with the logit bias set for several tokens concurrently. The algorithm progresses in rounds, where each round includes querying the API with the logit bias set for multiple tokens. By accumulating linear constraints obtained from these queries, we can efficiently determine the logit values. At the end of each round, we compute the smallest and largest possible values for the difference between the logits by solving a linear program over the accumulated constraints. This process helps us refine the interval enclosing the logit differences in each round based on the new information gathered. After a certain number of rounds, denoted as T, we provide the most precise bounds on each logit. If the logit differences for all tokens lie within the interval B, 0, the algorithm returns intervals alpha_I, beta_I, such that the logit differences for each token fall within alpha_I, beta_I. The computational time for each round of the algorithm is O(n³), excluding the API call computations. The algorithm maintains the invariant that the logit differences lie within alpha_I, beta_I, in each round. By induction, we can prove that the true logits always satisfy the accumulated constraints. The computation complexity for maintaining the logit difference intervals is O(n cubed, as shown by formulating the problem as a shortest path problem on a weighted graph. By transforming the problem into a shortest path problem, we can efficiently compute the exact intervals, alpha_I, beta_I, for all tokens after each query. This approach ensures feasibility and efficiency in determining the logit differences, making the attack more effective. Section Summary. Improved log-prob-free attack. Hyperrectangle Relaxation Center presents an enhanced method for modifying the logit bias of multiple tokens simultaneously to improve attack efficiency. By querying the API with logit bias set for multiple tokens in parallel and accumulating linear constraints, the algorithm efficiently recovers logit values. Through rounds of queries and solving linear programs, the algorithm refines intervals enclosing logit differences, ensuring tight bounds on each logit value are obtained, with a computational complexity of O(n cubed for each round. Section. Improved log-prob-free attack. Better queries on hyperrectangles. In this section, we encountered an issue with the previous approach where some tokens were sampled more frequently than others, even when the prior for the logit vector was uniform. This imbalance occurred because the bias in the logit values did not divide the hyperrectangle into equally sized parts based on the argmax coordinate. To address this, we introduced a solution to bias the tokens so that the output token distribution is closer to uniform. Specifically, we biased the token with the smallest range to have a probability of exactly 1n+1, under a uniform prior over the hyperrectangle. We made a simple modification to algorithm by adjusting the logit bias calculation, which resulted in a significant improvement in performance, as shown in the table. Achieving balanced sampling of all output tokens can be done in various ways, such as tuning a parameter in the bias expression or solving for the exact logit bias that divides the hyperrectangle into equal parts. The modified algorithm demonstrated promising results in terms of the query's logit metric, approaching optimality. We then evaluated the effectiveness of our practical stealing attack by validating that the attacks could recover the full logit vector with limited queries. Our strongest log-prob-free attack proved to be highly efficient, recovering 18 bits of precision with just 3.7 queries per logit. Moving on to stealing parts of production models, we focused on 5 of OpenAI's models and implemented the improved 4 log-prob attack due to its efficiency and precision. Both our hidden dimension stealing and entire layer stealing attacks successfully worked for all 5 models, accurately recovering the model sizes. While we disclosed the sizes of 3 models that were deprecated, we withheld the size of the LMVTT GPT 3.5 turbo models as per agreement with OpenAI. Our full layer stealing attack also yielded weights that closely matched the actual weights, with minimal error, as reported in the table. Section Summary. In this section, we introduce an improved log-prob-free attack method that addresses the issue of uneven token sampling in hyperrectangles. By biasing tokens to achieve a more uniform output distribution, we modify the algorithm to outperform previous methods significantly. Our approach focuses on balancing the sampling of all output tokens, leading to a more efficient and precise attack strategy for stealing production language models. Section. Defenses. In this section, we explore various defenses and mitigations against potential attacks on transformer models. We can prevent such attacks by removing the logit bias parameter from the API, although this may lead to a loss of some functionalities. Another defense strategy could involve replacing the logit bias with a block list of tokens that the model cannot output. Additionally, architectural changes such as splitting the final layer into 2 layers with a nonlinearity in between could also help defend against attacks. Furthermore, we can post hoc alter the model's architecture by modifying the hidden dimension of the final layer or by adding noise to the output logits. Implementing rate limits on logit bias queries and detecting malicious patterns in queries are other potential defense mechanisms. These strategies aim to prevent adversaries from extracting sensitive information from the model. Looking ahead, We are motivated to further investigate this problem to demonstrate that model stealing attacks are not just theoretical but can pose real threats to large-scale production models. Future research directions could involve exploring ways to break symmetry with quantized weights, extending the attack beyond a single layer, and adapting to changes in API parameters that could leak logit information. Additionally, exploiting stolen weights to enhance other types of attacks or extracting more information about proprietary models could be areas of interest for future work.